All right, so we're in section 4.4, and we are going to figure out some things that we can learn from using congruent triangles. So we're going to say using congruent triangles. Now when we talked about, right at the beginning of the chapter, we talked about congruent polygons. And we said that in order to show that polygons are congruent, we have to show that all the corresponding sides match up and are congruent. All the corresponding angles are congruent. We have to match every piece up to show that the polygons are congruent. Well, what we've been doing for the last few days with triangles is we came up with some shortcuts that we can use. So we're only using some of the parts to show that the triangles are congruent. Side, angle side, a hypotenuse, leg. So usually we're only using 3 parts of our triangle to show that the entire triangle is congruent. What we can figure out, once we know that the triangles are congruent, that guarantees us that all the matching parts of the triangle are congruent. So if we know that the 2 triangles are congruent, all the corresponding parts have to be congruent. So we're going to say, we're going to write this long phrase, and then we're going to come up with some initials. Corresponding parts of congruent triangles are congruent. And instead of writing this all out, what we're saying is that if we know that the triangles are congruent, all the matching parts have to be congruent. We're going to use the initials, CPCTC. So instead of saying this corresponding parts of congruent triangles are congruent over and over and over again, we're going to say CPCTC. And what CPCTC is telling us is that the matching parts are just, it's just telling us the matching parts are congruent. Parts, there we go. So let's take a look at how we use this CPCTC idea. We're going to do a proof here. So we're going to start with our drawing. Here's our drawing. We'll label our points. I'm going to call this M, N, O, P, and Q. And what we're given here, what we know, is that MP, segment MP, and NQ bisect each other at point O. This one should be Q, sorry. The one in the middle here is O. This is Q. And we want to prove that segment MN is congruent to segment QP. So what we know is that these segments here in the middle bisect each other. What we want to prove is these segments over here on the side are congruent. Well, it doesn't seem like a lot of information to start with, does it? Not a lot to start with. But our plan is to show that the triangles are congruent. Not the plane, the plan. I want to show that triangle MNO is congruent to triangle PQO. If I can show that the triangles are congruent, then I know that the matching parts have to be congruent. So we're going to show that the triangles are congruent. So this is just takes a few steps to do this. It's not a hard proof. So we're going to say our statement and our reason over here. So the first thing that I'm going to say is that segment MO, and as we do this, we'll make our marks on our triangles. Segment MO is congruent to segment OP, and segment NO is congruent to segment OQ. So let me mark those. I'm going to say these, and these are congruent, and this is congruent. What would be the reason that those segments are congruent? They're on a line. What does our given tell us? Okay, so bisect means cut in half, right? So if they bisect each other, each half has to be the same. So you could say, you could write a little explanation of that, or you could just say this is not given. It's given that they bisect each other. We're not given that they're congruent. But the fact that they bisect each other tells us they're congruent because that's the definition of bisect. That's what bisect means, is that they cut each other in half. That's a definition of bisect. But what else can we figure out now about those two triangles? What parts can we say are congruent? Well, what do we need? We need to use one of our postulates or theorems for triangles. So we need to use angle, side angle, hypotenuse, leg, something like that. So looking at our picture, what else could we figure out? Are there any angles that we could show are congruent?
Yes.
Which one?
The ones in the middle.
There we go. Very nice. These ones in the middle are congruent. So let's write those down. Yes. These we don't. There's nothing there that would tell us that those angles would be congruent. Oh yes, these two. Yeah, we could do those. But those aren't inside the triangle. We'd want them to be inside the triangle. So I'm going to say that angle MON is congruent to angle, oops, I forgot my angle sign, angle POQ. And Preston said that is because they are vertical angles. All right. So now, what postulate do our triangles match up with now? We have a side, an angle, and a side, and a side, an angle, and a side. So now I can say that triangle MNO is congruent to triangle PQO by side, angle, side. And now we know that the triangles are congruent, so all the matching parts have to be congruent. So I can say segment MN is congruent to segment QP by CPCTC. Corresponding parts of congruent triangles are congruent. So this is how we're going to use congruent triangles to figure other things out. So all we knew to start with is that these two lines bisected each other, and we were able to figure out that these two segments are congruent. So we're starting to bring together the different things that we know about different situations and bringing them all together. Here we use vertical angles, we use bisecting, we might have to use parallel lines to figure things out about angles. We might have to use a rectangle, rhombus to figure things out about sides. So we have lots of tools that we can use to figure things out about shapes in different arrangements and figure out how they're connected. So we're starting to bring the stuff that we know them all together. Any questions on this proof? All right, so let's move on to a couple of other things that congruent triangles help us figure out. We're going to talk a little bit about isosceles triangles. Anybody know what an isosceles triangle is? Yeah. Go ahead. Okay, triangle with two sides that are the same length. We're going to be just a little more specific, and we're going to say an isosceles triangle with at least two sides the same length. And the reason we say at least is because if all three sides are the same length and two of them are still the same length, then we call that triangle an equilateral triangle and it's isosceles. So we're going to have a triangle with at least two sides the same length. So here's our picture. So we have these two sides the same length. Now we use some special names for the parts of isosceles triangles. This angle is called the vertex angle. And the two angles down here are base angles. This side is the base, and the congruent sides are the legs. So this is what we mean when we talk about an isosceles triangle. It has to have at least two sides the same length. And we've used what we're going to talk about with isosceles triangles. We've used it before when we did angle puzzles. We've used this idea before. But we're going to talk about the isosceles triangle theorem. So when we did angle puzzles, what did we say we knew if two sides were congruent? What did we say we knew about the two angles? If these two sides are the same, what does that tell us about these two angles? They're the same. So that's going to be our theorem, is that if two sides of a triangle are congruent, then the angles opposite them are congruent. So if I drew that in on my diagram, that would tell me that this angle is congruent to that angle. So the base angles are congruent. So if we know two sides are congruent, we know the two base angles are congruent. It turns out that the converse is also true. And how do we make the converse of an if-then statement? flip them, switch them around, change the order. So we're going to say if two angles of a triangle are congruent, then the sides opposite them are congruent. So we can use this information both ways. If you know the two sides are congruent, that tells us that the two base angles have to be congruent. If we know that these two angles are congruent, then we know that opposite sides are congruent. So when we have an isosceles triangle, we have some nice information that we can work with. And we're going to talk just a little bit more, even a little bit more about what we can figure out about isosceles triangles. Any questions before we go on? So again, we're kind of bringing together information that we've used kind of here and there, bringing it all together as we talk today. All right, so a couple of other things that come from working with isosceles triangles. We call these extra things corollaries. Just another way of saying extra stuff that we know. So a corollary is just something that we can figure out easily once we know something. So these are our corollaries. Our first corollary is all angles in an equilateral triangle are 60-degree angles. And an equilateral triangle, what does that mean? All sides are the same. So let's draw a picture here. Here's my triangle. So if I have an equilateral triangle here, all these sides are the same. Then all these angles have to be 60 degrees. So that's our first corollary, our first bit of extra information we can figure out using isosceles triangles. Our second one, it takes a little bit to describe. It sounds a little bit complicated, but it's really not that complicated. The bisector of the vertex angle of an isosceles triangle is the perpendicular bisector of the base. So let's draw a picture of what this is telling us. So here's my isosceles triangle. And I'm going to draw the bisector of the vertex angle. And the bisector means it does what to the angle? Cuts it in half, so this angle is the same as this angle. The perpendicular bisector, perpendicular means what kind of angle? 90 degrees. So this angle is 90 degrees. That angle is 90 degrees. and it's the bisector of the base. So it cuts the base in half. So what this is telling us is cuts the vertex angle in half. And the base is cut in half at 90 degrees, at a 90-degree angle. So if I cut the vertex angle in half, I end up cutting the base in half at a 90-degree angle. And we know because we said this was an isosceles triangle, so these sides have to be congruent. And that also tells us that these angles are congruent. So we have all kinds of information now about this triangle because it's isosceles, and we've cut the vertex angle in half. Questions on that? Okay, let's look at a quick example of using isosceles triangles, and then we will be done. So here's our picture. And we have, I'll call this point B, A, and C. This is 30 degrees. This is 60 degrees. And this side is 10 centimeters. We want to find the length of segment BA. So we're looking for the length of this segment. So what can we do here? How could we start? Yes. Okay, very good. So Evangelique says, let's look at this. These two angles are a linear pair, so they have to add up to 180. So this angle has to be 120 degrees. All the angles inside the triangle have to add up to what? 180. So 120 plus 30 is 150. So what does that leave for this angle? These two angles are the same. So what does it tell us about these two sides? They have to be the same because that makes it an isosceles triangle. So that side would be 10 centimeters also. So segment BA is 10 centimeters. So a lot of times with these problems we have to do several steps before we can figure out the answer we want. We have to work with, like I said, we might have to work with linear pairs, we might have to work with vertical angles, we might have to work with parallel lines to get the information that we need to solve our problem. It's not just going to be, oh, I can figure it out just straight off from what they give us. Questions on this example? Okay, let me put the homework up and then we'll go over today's homework. All right, there you go.